This video is an overview of our IROS 2022 paper, Geometric Calibration of Single Pixel Distance Sensors. Our goal is to determine the 5-degree of freedom pose of a single pixel distance sensor attached to a robot arm using known robot motions and sensor measurements. Single pixel distance sensors return a single distance measurement to the object that they face. These sensors are small, low power, and low cost. These sensors are often placed on a robot and used for collision detection and avoidance. Sensors may be placed in arbitrary configurations, and during development, sensor configuration may change frequently. It is very difficult to manually measure the pose of these sensors relative to the robot that they are attached to. There are 5 degrees of freedom to measure. The origin is typically inside the robot volume, and orientation is very difficult to measure relative to the robot's orientation. As a result, most existing work utilizing single pixel distance sensors assumes that sensor pose is not precisely known. However, in order to reconstruct scene points, it is important that sensor pose is accurately known, as small errors in sensor pose can manifest as large errors in interpreted scene points. Due to this weakness, many tasks such as environment mapping, localization, and precise collision avoidance are infeasible with single pixel distance sensors alone. In this work, we consider a single pixel distance sensor attached to a robot arm, and show that it is possible to recover the sensor's 5-dimensional pose relative to the robot via an easy-to-perform calibration procedure. Additionally, we empirically characterize 2 distance sensors to evaluate how much they deviate from the idealized sensor model that our calibration procedure is built on. We evaluate the calibration procedure both in simulation and in the real world. Our calibration procedure is easy to run and has no additional hardware requirements. The only requirements are known robot motions, that the sensor makes multiple observations of the same plane, and that it is known which rigid robot segment the sensor is attached to. We use nonlinear optimization to recover the sensor pose relative to the robot segment that it is attached to, and recover the parameters of the observed plane. We include methods to avoid local minima during optimization. While not theoretically guaranteed, these methods have not failed in the real world. We provide an open source implementation of our calibration software. The distance sensors that we consider do not measure distance along a perfect ray. Instead, they have a finite conical field of view, which may introduce structured errors to their measurements. To better understand this error, we perform an experiment in which we change the sensor's angle of incidence with the plane while maintaining the same idealized distance. This experiment reveals that both sensors are sensitive to oblique measurements beyond 40 degrees. Therefore, when performing the calibration procedure, we avoid oblique angles beyond what the sensors are robust to prevent systematic errors. We evaluate our calibration procedure in simulation under controlled noise conditions. We find that, given fixed sensor noise, more observations lead to lower error in the recovered sensor pose. We also find that, given the same number of observations, additional sensor noise leads to higher error in the recovered sensor pose. We evaluate our procedure in the real world by attaching a single pixel distance sensor to a robot arm. We calibrate 16 times, each under different conditions. To measure the precision of our procedure, we cross-validate between trials in which the sensor pose remains fixed. The resulting precision numbers show that our procedure more precisely recovers the pose of the more optically robust VL53L3CX distance sensor. However, both sensors are recovered with sub-centimeter precision in position and better than 2-degree precision in orientation. While these results quantify the precision of our method, they do not directly measure its accuracy. We assess the accuracy of our recovered poses indirectly by assessing their performance in a downstream task, 3D scene reconstruction. For each calibrated sensor pose, we point the sensor at a previously unseen plane 32 times from different robot poses. We then project a point outwards from these robot poses according to the true observed measurement and calibrated sensor pose. We fit a plane to these projected points and measure the average residual from the point cloud to the best fit plane. In each trial with the VL53L3CX sensor, we see an average residual of less than 2 millimeters, indicating a high-quality reconstruction of the previously unseen planar object, which indicates that our calibration procedure is effective. Error in these reconstructed planes can come from either error in sensor calibration or from sensor noise. To test the source of our error, we add small perturbations to the calibrated sensor poses and perform the same projection and plane fitting procedure. The resulting residuals of these perturbed poses are shown in orange. In almost every case, our calibrated sensor pose reconstructs a plane better than the perturbed poses, indicating that our procedure is in fact accurate, and error in the residuals comes primarily from sensor noise. There are many practical uses for our calibration procedure. Our method makes practical a number of applications for single pixel distance sensors, which require precise interpretation of sensor measurements. For example, using these sensors for collision avoidance or robot localization. Our procedure also speeds up the development process by making it easy to reconfigure sensors and find their pose. In summary, this work presents an easy-to-perform procedure that enables the recovery of the 5-dimensional pose of a single pixel distance sensor mounted on a robot arm. We perform an analysis of the structured errors present in these sensors and provide results for our calibration procedure's precision and accuracy.